Hey guys, so we're picking back up with the effect of temperature on equilibrium. Okay? So the first thing you need to decide though is what type of a reaction are you talking about? Because we have two different types of reactions when it comes to heat, right? Because heat could either be consumed or absorbed, and in that case it's an endothermic reaction, or heat could be produced or released. And in that case, it's an exothermic reaction. So endothermic reactions require heat, exothermic produce heat. So the easiest way to do this is to first identify what type of reaction you're talking about and then treat heat like a reactant. So in an endothermic reaction, heat is necessary, which means heat is a reactant. Okay? And what did we say before? If you add something, it shifts away. So if heat is a reactant, it's going to shift to the right towards the products if you add it. And if you remove heat from an endothermic reaction, it's going to shift to the left towards the reactants, right? And here's some picture examples, right? So in this reaction of N2O4 to NO2, this is an endothermic reaction. How do we know that? Because heat is a reactant. Or what's another way we could say that something's endothermic? Well, you could say it's endothermic, right? Or positive delta H, right? A positive delta H also corresponds to something that's endothermic, right? But if we increase heat on an endothermic reaction, it's going to shift away and it's going to become more of the NO2, which is why this becomes brown. Whereas if we remove heat, since it's a reactant, it's going to shift towards the reactants, and hence why we get the colorless solution. But it matters here because what if this had been exothermic? If it's endothermic and you add heat, it shifts to the right. But if it's exothermic, then heat's over here. So if you added it, it would shift to the left. So misclassifying if something is endothermic or exothermic completely flips all your shifting, right? So because if it's exothermic, heat's over here as a product. So adding heat shifts it to the left. Removing heat shifts it to the right. Now, don't get too wrapped up on how K changes. If we had had more time and we were actually in the classroom, I might would focus on this a little bit more. But what I do want you to know is this. Capital K changes here numerically for everything we've just talked about. Adding or removing heat from an endothermic reaction, adding or removing heat from an exothermic reaction. If you change the temperature, you change capital K. That's what I want you to know. Okay? All right. The last thing we need to talk about here is catalyst, okay? So catalyst, you remember last chapter, we talked about their importance when it comes to kinetics, right? Because if you add a catalyst, it provides an alternative pathway, usually by increasing the number of steps. It slows down the rates for both though, right? It slows down the rates for the forward and the reverse to the same degree. And since capital K is the comparison of the rates of the forward and the reverse, and if they're both diminished by the same amount, would capital K change? The answer is no. Sure, you sped it up, but you increase the rates both, so the equilibrium isn't changed. Catalysts do not affect the position of an equilibrium. Let me say it again. Catalysts do not affect the equilibrium. Okay. All right. So this is a table that I made for you to kind of help you, right? So notice only one thing has an effect on K, and that is changing the temperature. Right? Changing the temperature. That's the only thing that affects K. And if you add a reactant, it shifts to the right, away. If you add a product, it shifts to the left, away. If you remove a reactant, it shifts to the left, towards where you removed. If you remove a product, it shifts to the right, towards where you removed. If it's an endothermic reaction, then heat is a reactant, which means if you increase the temperature, you are increasing the heat, which means it's going to shift away to the right. If you decrease the temperature, you're removing heat, so it's going to shift to the left towards the heat that you removed. In an exothermic reaction, heat is the product. So if you increase the temperature, you're increasing the heat, so it's going to shift away towards the reactants. If you decrease the temperature, it's going to shift towards the products. So it'll shift to the right. All right, what about if we change volume? Well, it depends upon which side has more moles of gas, right? Because if you increase the volume, then you decrease the pressure, so it needs to shift towards the moles. That's more, right? If you decrease the volume, then you've dramatically increased the pressure, so it needs to shift to the side with less moles. So let's look at an example here. So here we have the equilibrium of 2 moles of SO2 plus a mole of oxygen goes to make 2 moles of SO3 gas, okay? And it says delta H is equal to negative 198 kilojoules. What's that negative telling you? Yeah, exactly. It's telling you that it's exothermic, all right? All right, so what if we add more oxygen to the container? Oxygen is a reactant. If we add it, it's going to shift away, so it'll shift to the right. What about if we condense and remove SO3? Well, if I am removing a product, it's going to shift towards where I removed, so it's still going to shift to the right. What about if I compress the gases? Compress means diminish the volume. If you diminish the volume and you have dramatically increased the pressure, so we got to figure out, we need to bring the pressure back down. Which side has less moles? Okay, the left side has 2 plus 1 is 3. The right side has 2. So we're going to shift to the right because that's the side with less moles. What about if we can cool the container? Well, we got to come back here to this delta H. The delta H meant the negative says that it's exothermic, which means heat's going to be a product. So if we are cooling it, we are removing heat. So I'm removing a product, which means it's going to shift towards where I removed, which means it shifts to the right. So there's a lot of ways that you can say shift to the right. Okay, because we've just said 4 different ones. What about if we double the volume of the container? Well, if we're doubling the volume, then we are dramatically diminishing the pressure, so it needs to go to the left, to the side with more moles, to bring the pressure back up. What about if we warm it? Well, we've already talked about how heat is a product. If I increase the concentration of a product, it will shift away to the left. What about if I add helium to the container? Is helium in this anywhere? No. And what's the deal with helium? Helium is a noble gas, which means it's inert, it's unreactive, so it's not going to do diddly squat. And what about if we add a catalyst? We talked about that too. Not going to do diddly squat, right? Because it's going to speed up both rates. Okay? So it's not going to make a difference. All right, stay with me. I'm going to pause the video real fast. Hey guys, so I paused and I changed the slide. So I want to do some more practice with you on Le Chatelier's principle, because what we just did was one in which it was homogeneous, meaning it was all gases. But what about something like this? What about if it's heterogeneous? Well, what if I said that you were to add water to this? What would happen if you added water to this? How would it shift? It wouldn't. It wouldn't shift. Why would it not shift? Because water is a liquid and liquids do not affect K, right? It does not appear in this K expression. Thus, adding water, removing water is not going to make a hill of beans different here. Also, it's important because if I were to ask you, hey, how would it shift if we doubled the volume? If you double the volume, you cut the pressure in half, it needs to shift to the side with more moles of gas, right? Because you may originally look at this and say, oh, well, it's 2 and 2, it's not going to shift. But remember, we don't care about this. Scribble through this. This doesn't make any effect on it, right? So it's 2 moles versus 1 mole. It's going to shift to the left because we doubled the volume, which means we cut the pressure in half. So it needs to shift in the direction of more moles of gas. So it's going to shift to the left. So my recommendation, again, when you get a heterogeneous reaction like this, or like this, and I ask you Le Chatelier's questions on it, go ahead and scribble through, oops, sorry, not that one, woo, scribble through the solids. So the tin 4 oxide, delete it. And the tin, delete it, right? This is an equilibrium between carbon monoxide and carbon dioxide. That's it. That's the equilibrium. Okay? Adding tin doesn't do anything. Removing tin 4 oxide doesn't do anything. Why? Because it does not appear in this K expression. All right. So that's it on Le Chatelier's principle, and that's it on the material for your test on Wednesday, okay? So we have covered now all the material for your test Wednesday. If you have any questions about this stuff, you need to be commenting in the discussion for the lecture, okay? Also, if you have any homework questions, please use that discussion. Several of you guys have been using it to check your homework, and that's great. That's brilliant. I've been commenting in there as well to try to help you. Keep it up. All right, but test Wednesday on chapters 14 and 15. Stover out.